Hi, I'm Carlien and I'll be discussing our project on the corrosion characterization of solid and lattice aluminium silicon 10 magnesium manufactured by laser powder bed fusion. A quick look at key points in additive manufacturing for this presentation. For metal AM, we speak about 3D printing of metals, in this case with laser powder bed fusion. It can create custom and complex geometries, reducing how much assembly is required and decreasing lead times. However, there are some process-induced defects, such as surface roughness and porosity. I will lay out the hypothesis, show the samples, give an overview of the experiments, and discuss results, conclusions, and recommendations. The hypothesis is divided into 4 parts, namely, that there will be different corrosion effects for different porosity contents and surface roughness conditions. Process-induced porosity will play a crucial role in the corrosion progress, specifically relevant to complex designs like lattice structures. Higher corrosion resistance is expected for smaller amounts of porosity and for smoother surfaces. And analyses of these corrosion effects will enable optimization of the process parameters for desired outcomes in additive manufacturing and laser powder bed fusion. Here are the solid and lattice samples, with the varied process parameter being laser power. E1 refers to the lowest laser power and E5 is the highest laser power. For the solid cubes, the pins on the left of the samples refer to the laser power used to produce the samples. The pins on the right indicate the number of the sample in its respective laser power set. The lattice cubes in the right image were marked on the side using the same numbering convention as the identifier pins for the solid cubes. For the experiments, the considered defects were surface roughness and porosity, with surface roughness done only on the solid cubes. Corrosion testing for neutral and acetic acid salt spray was carried out for 7 days with a 5% sodium chloride solution. For the neutral salt spray, the pH was between 6.5 and 7.2, and for the acetic acid test, the pH was between 3.1 and 3.3. Compression testing was carried out only on the lattice cubes. The first tests were for surface roughness. As the top surface is the final layer of the laser powder bed fusion process, it is likely to be the most affected by the process parameters. The bottom surface was excluded as it was not representative of the parameters, due to the samples being manufactured on supports, which lead to an irregular surface. The average surface roughness per laser power is shown as a text insert above each image. The surface roughness decreased from 23.7 micrometers at the lowest laser power to 10.6 micrometers at the highest laser power. The first two top surfaces are seen to have a much higher surface roughness than the last two, which corresponds to lower and higher laser power respectively. The values themselves were obtained using optical microscopy with an Olympus DSX 510. In this instance, the surface roughness value is not dependent on track orientation relative to scanning, as it uses SA, which takes the line roughness profile parameter RA and expands it 3-dimensionally. The trend for surface roughness is seen in Figure 3, where it shows a general decrease with an increase in laser power. The reason for this decrease in surface roughness is most likely due to wider and more overlapping melt pools, which create a relatively smoother top surface. The error bars show that the surface roughness varied greatly in each laser power set. Color scale maps were created using the Olympus Stream software and show the height variation in surface in a 3D view as well as in side view. Both views show a larger variation in the surface roughness for the lowest laser powers, and a smoother surface, less height variation at higher laser power. With porosity, Table 1 and Table 2 show the porosity percentage obtained from the CT results, corresponding to each laser power set, as well as the relationship between the two in a graph insert in Table 1 for the solid cubes and Table 2 for the lattice cubes. The same trend is seen for both, where the lowest laser power E1 has slightly more porosity than E2. This can be explained as due to lack of fusion porosity at E1 and ideal melting with the lowest porosity content at E2 compared to E1. As laser power increases further, the total amount of porosity increases, which is due to more keyhole porosity and consistent with previous work done by Prof. Anton du Plessis. CT slice images again show this trend in porosity for both the solid and lattice cubes, with increased microporosity clearly seen in the struts with higher laser power in the zoomed-in areas of the lattice cubes. The encircled areas in Figure 5 also show the presence of high-density inclusions, which could potentially be due to contamination from the powder itself. Using Volume Graphics VG Studio Max, the porosity is identified and quantified, as shown here in a 3D image, where the higher laser power samples are seen to have much higher porosity and the pores are more spherical in shape, whereas the lower power samples have less porosity, which is less spherical and lack of fusion type pores. This was done for a region of interest of 4 by 4 by 4 millimeters cubed. After the defect analysis, corrosion testing was started. Figure 8 shows the samples after 7 days in the neutral salt spray, where some corrosion product has formed, but visually alone it cannot be said what the extent of corrosion is. Figure 9 shows the acetic acid salt spray samples after 7 days, where it is seen that more extensive corrosion product formed than with the neutral test. This corrosion product was studied closer, and what formed on the samples looked gelatinous directly after they were taken out of the salt spray chamber. When it fully dried out, it was chalky in texture. Elemental analysis with SEM-EDS picked up high levels of oxygen, but phase analysis with XRD did not find any crystalline phases of oxides or hydroxides. This suggests the corrosion product is amorphous, most likely amorphous aluminium hydroxide. An important note from literature is the high volume ratio of corrosion product to corroded metal, in the order of 6.5. The aligned CT images for before and after corrosion clearly show the corrosion product that formed. Here it is shown for the lowest laser power solid cube, and here for the highest laser power solid cube. It is also clearly seen in slice images for the lattice cubes at the lowest laser power and the highest laser power. As these are single slice images, they are not representative of the amount of corrosion experienced over the whole sample, and no comparison can be drawn between the corrosion at different laser powers. For the lattice cubes, Figure 15 shows the compressive yield strength versus laser power for before corrosion, after the neutral salt spray, and after the acetic acid salt spray. The graph shows the general trend for all three situations. The compressive yield strength was taken as the maximum compressive stress reached at the peak of the initial linear elastic region, and can be seen to vary slightly between laser powers as well as after each corrosion test. The actual values show a difference of almost 9 megapascals between the maximum and minimum strengths for before corrosion, 7.6 megapascals for after the neutral salt spray, and 11.7 megapascals after the acetic acid salt spray. The higher difference after the acetic acid test compared to the neutral test can be attributed to more corrosion product present in those lattices than in the neutral test lattices. The possibility is that crack initiation sites are filled with corrosion product, delaying the onset of cracking and failure. From this project, it was concluded that corrosion can clearly be seen with CT scans and visualized with aligned slice images of before-after corrosion states. Porosity did not affect the corrosion during the early stages, namely the first 7 days, nor did the surface roughness have a great effect. The varied laser power did not strongly affect corrosion, despite inducing differences in porosity and surface conditions, and the possibility remains that crack initiation sites are filled with corrosion product, delaying the onset of cracking and failure, and thereby slightly increasing the compressive strength of the samples. In order to gain an in-depth understanding of the effect defects such as porosity has on the corrosion of these alloys, it is recommended that corrosion testing is carried out for longer than 7 days. A larger sample size is used to allow more samples per laser power set for different tests. Further in-depth CT scans are performed to verify whether there was more corrosion product formed at higher laser powers, and polarization studies to determine pitting and repassivation potentials as a function of sample porosity percentage and surface roughness. This is so that it can be determined when in the corrosion test pitting is expected to occur and when the passivation takes over. Thank you.